Duh. Having a dull moment. All right, let me go back to share screen then. All right. Picking up with the conversions. The two that were in number 4 are one-step conversions. You can use a website. You can use the conversion table that's in the back of your lab book. For the first half of that problem, you should get just over 82 yards. I did not specify that you needed to give the answer in sig figs, so I didn't really care if you reported it in sig figs or not. And then the 11 ounces should end up being 311.88 grams. Again, I didn't really pay attention to sig figs for this one. Then we get to the multi-step problem. There's actually more than one way to do this and get the same answer. I did it one particular way. That's not the only way. So I started out with the idea that I knew how big the tank was, 250 gallons. I also knew my gas mileage. I get 8 miles per gallon. Obviously, the mileage really sucks on this thing. But that means if I burn through my entire tank, which is actually part of the end of the problem because it says, how far can it go on one tank? So you can go 2,000 miles, but it's kind of putting, okay? It's not very fast. I gave you 450 feet per 12 seconds. This is something that doesn't have a 1 on the top or the bottom, so you actually have to keep track of all your numbers. I converted from feet per second. First, I went second. I converted my seconds into hours, and then I dealt with my, I really would like to know how many miles per hour. So I get about 27.5 miles per hour, because first my seconds will cancel out, and then my feet will cancel out. And I still have a top and a bottom, though. I still have miles per hour. I can flip that upside down so that my miles cancel out. 2,000 miles per tank. 1 hour is 25.5. So it takes me 78.2 hours to burn through my entire tank full of fuel.
If our work showed the decimal point numbers, but then because I saw 12 seconds, so I reported my answer in 2 significant figures. I did 78 hours. But
that's fine. That's fine.
Okay, cool.
You can bless my child for this problem. He is an avid D&D fan, and of course he took both semesters of chemistry since he's a mechanical engineering student. And one night when he was waiting for me to get out of class, he's like going, I have a problem. And he starts doing it on the board, and he's like going, isn't this a really cool dimensional analysis problem? And I'm going, oh yeah, I think I'm going to keep that one. Because it takes into account a batch of different dimensional analysis. Things have to cancel out. All right. I want my thing to scroll. All right. Then we get to temperatures. So 550 Fahrenheit over to Kelvin. Do it in 2 steps. First, convert your Fahrenheit to Celsius. Subtract your 32. Multiply by your 5/9. This gives you 287.8 on your Celsius. Add your 273. Ultimately, you get 560.8 for Kelvin. Then I gave you one that actually goes in the opposite direction, and I gave you a negative. So you have to make sure you keep track of your negative. So negative 17 Celsius, multiply by 9/5. This is the upside down version of it. Then add your 32, you get 1.4 Fahrenheit. Now, one of the things I noticed about number 7 is some people did not grasp that a piece of steel deck plating has 3 dimensions. It's like a big thick tile. So it's 12 inches by 12 inches by a quarter of an inch. So I saw a few people who made errors of they multiplied the 12 times the quarter and didn't embrace the third dimension. So that gives you a really weird volume. The idea, of course, being that if you have centimeters times centimeters times centimeters, you have cubic centimeters as your volume. And you ultimately get 589.9. I gave you pounds, 10.2. When you convert that into kilograms, you get 4.64. But I wanted grams per cubic centimeter. So I need to multiply by 1,000 to get my kilograms over into grams. And then my final step is the division step. 4640 divided by 589 gives you 7.86, give or take a tenth, depending upon how much rounding you did in the process. I thought, given all of the things that have happened this year, a toilet paper problem ought to be like topical. So I looked up a density for tissue paper to use as my value for this problem. And it's strictly a rearrangement of the density equation. You know what the density is, you know what the mass is, volume is your unknown. It's a big fluffy roll of toilet paper, one of those double roll things. You get 1,536.4 cubic centimeters. And then we get to a few of the kind of leftovers at the end here. Scientific notation, trying to make sure you are keeping track of where you should put your decimal point. We're going to get 3.4 times 10 to the fourth, because you are moving your decimal 4 spaces. Then I gave you a small number, so this one has to have a negative exponent. You get a negative third to go with your 9.1. Qualitative versus quantitative. Remember that quantitative means numbers. So cobalt things are pink, that's qual. If you have 46 milliliters, that is quant. And then last thing, obviously we're not, except for when you come to lab, we're not spending much time on Granby Street. But presumably there'd be a variety of cars and maybe a couple of pickup trucks and maybe occasional motorcycles. So heterogeneous for vehicles. Mountain Dew should be homogeneous because we've got, a liquid that is carbonated, but presumably, unless you leave it sit around for hours, it's pretty much the same all the way through. And then the key word to the last one there is the word solution. Things that are solutions need to be homogeneous. So questions about Chapter 1's homework set.
Yeah, I got one on 8.
Okay.
Yeah, so I showed the math and I got the right answer, but I don't know. I'm pretty certain it's pretty late when I did this. So I wrote 158 centimeters cubed, and right before it I have 1576. So I don't know. Heavy eyes. I must have just not been thinking and wrote it. But do you give some credit?
I wrote a lot of people. I wrote comments on. I'm assuming you guys can see the comments when I do grades, because it gives me a box and it says put comments in this box. And so a lot of times I'll put like error in volume or error in something else. So I might have written comments if you wrote it 2 different ways. You might want to go back and check.
Yeah.
And it was only worth 2 points, so it was not a heavily weighted problem anyway. Other questions regarding Chapter 1's homework?
Same on number 8. How did you get 1536? Every time I type in the calculator, I get 1576.
Did I do it wrong? Let me look for my calculator. Let's see.
No, I'm typing it in wrong.
So 1.44, because that's your density. And then you're flip-flopping it, so actually it's 227 divided by, actually my calculator is sort of misbehaving on me here. No, I actually have, yeah, it is supposed to be 1576.
I was like, wait a second. I typed in like 3 different calculators.
Which means I need to go back and look at submissions. Let me write myself a note here. This is, part of this is due to the fact that I usually do all my answer keys by hand, and this may be a transposition error on my part. So this is number 8. I will go back and have a look at submissions, because obviously I have a digit wrong there, which makes me think I transposed it when I copied it from the sheet of paper I had done them on over to do the digital answer key, because I figured it was easier for you guys to read if you didn't have to put up with my awful handwriting. And so, like I said, I did them by hand, and then I typed them into my homework set document. So yeah, I will go back and check that one. That one is it looks like a transposition error. Since a lot of you have me for lab, I also ran into a problem with the fact that the way that the quiz function of Canvas works, if you don't spell the answer the way I put it in, it counts it wrong. So I went back and manually corrected a whole lot of the ones that had to do with the word desiccator. Because I was going to change the answer key, but then it gave me some bizarre message, which I wasn't entirely sure what it was going to do. So it was easier to actually go back and manually change the point values from right to wrong. I mean, from wrong to back to right. So hopefully I did all of that correctly.
I got 1576 on number 8 too, but you didn't mark it wrong.
I couldn't tell if you marked it wrong or not. Like with mine, I can't see. I see the commas, but I can't see which ones
you marked. See above it where it says grade?
Yeah, if I...
Because
like I said, some of them I put comments in for more obvious errors. Some of them I didn't. It's a really hard system to deal with. I will go back, however, since I only have 20 students, I will go back and skim through all the homework submissions though and see what is in your files, so that I can make corrections as needed. Yeah, the whole transposition, it's like, I'm trying to embrace the whole doing everything digitally really hard, but because I have a lot of answer keys and things that are handwritten, sometimes, yeah, I think transposition stuff happens. I will go back and work. I will go back and see what I can do about fixing it though, because I did realize I did fix the desiccator problem for lab. So I'm working on the rest of it. All right, let me stop this share and pull open notes for chapter 2. We are about 60% of the way through that chapter. All right, let me see about screen sharing again. All right, so we're already down through. Started ions. All right. think this is the last bit that we were talking about last Thursday. We were looking at the cations, keeping in mind that all of them are positive because they have lost electrons. Our anions gained electrons. So not only does that make them negative, it also changes their, we'll call it a suffix. Because once you have added those electrons, the way the nomenclature rules work, you are getting a different ending. All right. And we talked a little bit about the pattern here. So when you are looking across the top of the periodic table and ignoring the transition elements for the moment, we will come back to them. Hydrogen column, also known as the alkali metal column, they all like to be +1s. The berylliums, all the alkaline earths like to be +2. Boron, aluminum, and the ones below it sometimes like to be +3. Boron, aluminum, definitely. The ones below it are a little bit iffier. Carbon, silicon, some of the other ones are ±4, but carbon and silicon are always ±4. Also think of that as like the top of the mountain, okay? You have kind of this peak that's not quite exactly in the middle of the table. It's a little bit more off to the right-hand side, but it's still kind of a peak on a hill. Nitrogen, phosphorus, and some other things are -3s. Oxygen column, -2s. Halogens are -1. And helium and all of those other noble gases are pretty much always 0 because they hate everybody and they hate to bond with anything. Right at the moment, we'll make kind of a blanket statement about the transition metals. They are positively charged. There are no negative ones. However, they are variable. And the pattern by which that variability occurs is not particularly predictable, except when they are in a molecule. So now we're going to start sticking things together, okay? If you want to make a compound, specifically if you want to make an ionic compound, we want a cation or 2 or 3 and an anion or 2 or 3. The whole big overall goal here is you want everything to cancel out. You don't want to have any leftover charges. You don't want to have any extra negatives or extra positives. So right at the moment, we're going to deal with a set known as the binary ionic compounds. Binary meaning that there are 2 elements, not necessarily that there are only 2 atoms. So let's pick on, I just realized I misspelled fluorine. It says fluorine on there. If you pick on sodium, sodium is in the alkali metal column. Sodiums like to be +1s. Well, fluorine, halogens, like to be -1s. So if you take one of each and you stick them together, basically they are trading an electron. The sodium becomes positive, the fluorine becomes negative. There's no leftover net charge. And you have a molecule that is 1 sodium, 1 fluorine. Well, what if you traded more than 1 electron? I picked on magnesium and oxygen. Magnesium likes to be +2s. Oxygen likes to be -2s. So again, we have kind of a equitable trade here. The exact same number of electrons that are being lost are this exact same number that are being gained by the one that becomes an anion. So you still have a 1-to-1 ratio, 1 magnesium, 1 oxygen. What if they don't match? So I'm going to try to use my whiteboard here and give you some pictures to go with this. Usually I have sticky things, magnetic sticky things that I use on the board. All right. I'm going to draw them. All right. Think of it like this. We have a sodium. Think of the little pointy bit as your +1 charge. If I have a fluorine, which we know is negative now, and it has like one divot cut out of it. So if I slid them together, they would actually match and I wouldn't have any leftovers. So I can do something awfully similar with my magnesium and my oxygen. And it looks kind of like this. We've got magnesium with 2 points. We've got oxygen with 2 cutouts. And if I slid them together, I'd have a nice little rectangle and there wouldn't be any leftovers. Now I'm reaching that one that had aluminum. So aluminum, like boron, likes to be +3. But I've still got an oxygen. All right, so there's my aluminum and my oxygen. So I'd have this problem of if I used 1 aluminum and 1 oxygen, I'm kind of somewhat out of luck in that one of the points on my aluminum doesn't have a match. It doesn't have a divot to stick into. So we begin to embrace what math refers to as the least common multiple idea. Now, there are 2 different ways to do this. I didn't have an easy way to draw arrows in my notes. So let's see if this works here. One of the things you can do is you can take the numerical part of your ion's charge and you can use it as a subscript for the other one. So since my aluminum is +3, I can then make it an O3 in my molecule. Since my oxygen had a -2 charge, I can use the 2 as the subscript for my aluminum. Now, as long as you have 1 even and 1 odd, this actually is a pretty straightforward number or a way to do it. Sometimes you will run into a situation where you have 2 odds or 2 evens. It's a little bit more complicated. So let me present another way to kind of deal with this. We're still utilizing the whole least common multiple idea. A least common multiple idea means that I want 6, because 2 and 3 divide into 6. And so if I have it like this, 2 aluminums gives you +6, 3 -2s give you -6. And I still end up with the same answer. I still end up with Al2O3. Both methods work. The only minor, we'll call it hiccup, with utilizing the swapping numbers point of view is that when you do that, like I said, if you have 2 numbers that are both odds or both evens, sometimes you end up with errors. You have to kind of double check your ratios. Remember in math, If you have 2/4, you're supposed to reduce it down to 1/2 because least common terms kind of thing. That actually also sort of holds true for doing this. So magnesium and bromine. To think about this for a moment. We saw magnesium above. Magnesium likes to be +2. Bromine is a halogen, just like fluorine, likes to be -1. I need 2 bromines so that I have 2 negatives in order to cancel out the 2 positives for my magnesium. And now we're kind of heading back in the opposite direction a little bit. As we're doing names of molecules, we have to use the same rules that we saw above when we were naming the cations and the anions. As we progress through binary compounds, there's 2 basic flavors. There's the ones that are a metal plus a non-metal. So this is why it's helpful that you have a periodic table and that you actually kind of note where the staircase is on the right-hand edge, so that you can know where the metals versus the non-metals are divided. You can actually have molecules also that are composed of 2 metal or 2 non-metals with no metals involved. And for general chemistry, we are going to pretend that 2 metals together is not possible. In reality, it is. Okay, you can have amalgams and things like that, and alloys. But for general chem, we're going to pretend that that's not an option. So how about full names? Full names are most often 2 words. It doesn't really actually matter if you capitalize the first one or not. It is, however, important that you put the cation portion of your molecule at the beginning and the anion portion at the end. There is one molecule that does not follow this rule, and it has a name all by itself anyway, so it kind of doesn't follow any rules, and that's known as ammonia. So magnesium bromide. When you look at the molecule, you see the subscript of 2 with the bromine, and yet when you look at the name, there's no indication. It's just magnesium bromide. It's not magnesium 2. It's not magnesium dibromide. It has no indication. It is, we'll call it, implied information. If you have the correct name of the molecule, it is both implied and assumed that you actually know what the name of, or what the charge of those atoms is when you are building the molecule. I'm looking, it's AlCl3, and yet on my monitor, this 3 is really scrunchy. I guess partly because it's a subscript. So AlCl3. Again, nothing to indicate openly what the presence of your 3. You have aluminum chloride, it's not trichloride. We're going to get into Roman numerals here in just a moment. There are no Roman numerals because it is what I usually refer to them as a normal metal. You may also see some textbooks refer to them as a main group metal, only to differentiate them from the ones that are transition metals. Strontium sulfide. Now we're back to the whole idea of, I actually traded 2 electrons, but that doesn't affect the name. I have a single atom of strontium and I have a single atom of sulfide. It doesn't make a difference. It's just strontium sulfide. And the Al2O3 that I built further up the page is just aluminum oxide. It has no 2s, it has no 3s, it has no dis or tris in its naming. A lot of this, like I said, is assumed and implied information. So now we're going to switch gears just a little bit to all that stuff in the middle that we've been kind of ignoring. The ones that are the transition metals. So things that we know, again, mentioned above, all the transition metals are positive. There are no negatively charged transition metals. They do not gain electrons. They're metals. They lose electrons. Most of them have at least 2 possible charges. Some of them have more, but pretty much all of them, there's a couple of exceptions. There's always exceptions to the rule. Pretty much all of them have at least 2. Now, how do you figure it out? If you have a naked cation shown, then you're just looking at the charge. But most of the time, they're contained within a molecule. So the molecule and what they are stuck to, the anion part, is kind of what helps you determine the charge. So remember all those famous dead guys that were back at the beginning of the chapter, and the fact that we talked a little bit about the Latin, Greek, German roots? That actually comes back again. It does have its uses. So Cu plus 2. We are primarily going to be using the Roman numeral system, also known as the stock system, where you use the name of the element and then you use your Roman numeral to indicate your charge. So I gave you 3 relatively common ones here: copper 2, lead 4, tin 2. So those are just examples. But now we got to circle back to that. There's more than one option. And definitely at some point, go back and compare the information in your lab book versus the information in the textbook. I think the presentation and the examples that are given in the lab book are actually a little bit better than the ones that are in the textbook. So kind of keep that in mind as we're going through the latter half of this chapter. Iron comes in 2 versions. There's a +2 version and a +3 version. There is no such thing as an iron 1. Now look at the second column there. Remember back, famous dead guys, okay, who spoke Greek and Latin? A lot of that, unfortunately, didn't go away, especially if you happen to be headed into a medical/health sciences profession. In the medical world, they hung on to all the Greek and Latin. If you've had A and P, you know how hooked on they are on all of the Latin names for bones and muscles and everything else like that. It kind of holds true with chemicals too. So iron 2 in the older but still used naming system is ferrous, because iron is ferrum. We're going to conjugate it, call it ferrous. There's a version called iron 3, a little bit higher charge. Again, hang on to the Latin root, put an ic ending on it, IC. And so you have ferrous and ferric to match the iron 2 and iron 3 as the 2 different naming systems. And I gave you another pair here to look at. There are more in the textbook too. and in the lab book. Here's another one that is a pairing. There is no such thing as, actually, I think I typed the wrong digit there. It's supposed to say PB plus 2 and PB plus 4. I'm squinting at my screen. I think I might have typed it wrong. It's supposed to be PB plus 4. There is no such thing as lead 3. Unlike iron, which is a 2 and a 3, lead is a 2 and a 4. Each individual element only has certain options. But if we go back and we start looking at the older naming system again, lead 2 is plumus, because plumum was lead, is lead. Because okay, a little more history thrown in here. Since the Romans kind of sort of invented indoor plumbing, they used lead pipes, which on the surface sounds like a really cool idea because lead is kind of soft and you can roll it out into a flat sheet, malleable, and you can bend it into a pipe and kind of heat it up and seal one side. And, oh, cool, you've got a pipe. Of course, we now in the 21st century are well aware that having lead pipes was a really bad idea. So you could in some ways attribute, among other reasons, lead poisoning as one of the reasons for the fall of the Roman Empire. But we hung on to the Latin root. Now, one of the problems that unfortunately comes along with the older system is there's kind of more memory involved. There's kind of more knowledge needed when you're using that older naming system. There is a rule, and the rule is printed there, but the rule is not as helpful unless you have a certain amount of pre-knowledge. Simply saying that the higher charged one gets the ick ending and the lower charged one gets the us ending only helps you if you know what the options are. Because like here, we're just looking at lead and iron, and they're not the same options. You know, one is 2 and 3 and the other one's 2 and 4. So knowing what you have available is kind of a necessary component. There is a certain amount of memory involved here in kind of assembling all the knowledge and being able to kind of like line it up. Just like the other ones that we've been looking at earlier, you don't usually get a lot of naked ions, naked cations. Usually they are part of a molecule. My recommendation is, and this sounds like you are doing them backwards, but this is the best way to approach the idea. Start with the right hand end of the molecule. So in this case, we are looking at FeBr2. So start with the bromine end and a periodic table. Look up bromine, note that it is a halogen and it likes to be -1. I have 2 of them. So the latter half of my molecule is worth -2. We're going back to that shooting, everything's got to be neutral at the end. So if I only have 1 atom of iron, it has to be +2, because otherwise it would not give me a neutral atom. So we can name this either by using the stock system, or we can use the older system. Note, the second word does not change. It is only the first word that is dependent on which system you're using. We're kind of focusing on the Roman numeral system. However, I have a fair number of examples of the older ones in here because I often have a lot of students who are either already in the medical field and continuing, or people who are heading into the medical field and The medical field hangs on to the older naming system. So we've got iron 2 bromide. Note, the
Quick
Roman
question.
numeral is in between.
Quick question.
Yes.
That compilation of terms that you have, is that something that you could possibly upload into the Canvas? You're saying you have a bunch of different terms. You said with those different types of rules and whatnot.
These are the rules.
No, the conjugations with the different elements. You said they kind of vary. You have a bunch of different examples. You said.
There is a relatively decent table full of them in your lab book.
Okay.
All of the common ones. Iron, lead, tin, copper, mercury, and a few others. And there's a reasonable number of them in your textbook.
Okay.
It doesn't apply to all elements because a lot of them don't have a Latin version. So there's really only about maybe eight or nine total. There's a couple that are in your lab book that are not in the textbook. This is kind of why I said lab book's a little bit better at this.
Okay.
All right, let's look at cobalt and sulfur. Again, start on the right-hand end. Sulfur is under oxygen on the periodic table. It's a -2. I have 3 of them. So I have 6 negatives. But I actually have 2 atoms of cobalt. So you have to be able to kind of divide your +6 that would be required in half, which means each of your cobalts is +3. Cobalt doesn't have a Latin version. It has an ic and an us, but it doesn't have a Latin version. It just has cobaltus and cobaltic. So since this one is the 3 version, cobalt 3 sulfide, it is cobalt ic sulfide. Only some of them have the Latin versions. Now the tin one, you actually are running into the, if you swapped your subscripts, you'd be in trouble. Because based upon your, and look at the name first, tin 4 oxide, that makes you think that you should have SN2O4, except you have to not have even numbers in the same molecule. And again, there's one exception. In peroxides, actually no, there's 2 exceptions. Peroxides and mercury, because mercury's weird in every way. All the other ones, you have to not have 2 evens in the same molecule. So tin 4 oxide, which came from oxygen is -2. I have a pair, so that's -4. Your tin, of which there is just 1, must be +4. Tin 4 oxide. And this is one of the Latin ones. Tin was stannum, so this is stannic oxide. Toothpaste used to have not sodium fluoride in it the way it does now. Used to have stannous fluoride in it, SNF2, till they eventually realized that giving everybody toothpaste with tin in it might not be a good plan. Not that you're supposed to eat it anyway, which is also, again, one of those things where, like, why little kid toothpaste is different than adult toothpaste. But things that change over time. That one's a lot more recent than the plumbing problem with the Romans. Make sure the Roman numerals only appear in molecules that have transition metals. No other ones. So let's look on AuCl3. Au, gold. But I have 3 chlorines. So this kind of goes back to that idea of chlorine's a halogen. Chlorines like to be -1. I've got 3 of them. So my gold needs to have a Roman numeral of 3 to go with the chloride. Or, back to Latin again, gold was aurum, A-U-R-U-M, and so it becomes auric chloride. There is another version of gold which is called aurus, that is +1. Now, there are 2 metals. There are 2 transition metals. And I think I spelled conspicuously wrong, or at least the word document seems to think so. Silver and zinc. They will not have an either or. Silver is always and forever +1. There is no other version of silver. Most textbooks, most modern textbooks, let's put it this way, most modern chemistry textbooks will go ahead and put the Roman numeral 1 in a silver containing compound, despite the fact that there is no other option. If you're in the medical field, if you ever had a nosebleed, one of the things that they do for nosebleeds sometimes is take this big old Q-tip that is dipped in silver nitrate and stick it up your nose because it basically burns the mucous membranes very slightly and helps control your nosebleed. But the bottle that they put that in is not labeled silver 1 nitrate. It's just simply labeled silver nitrate. The medical community, again, is the outlier here. They do not usually put the Roman numerals in. Zinc is the other metal that has no other options. Zinc is always and forever +2. If you are one of those people like me who sunburns appallingly badly, you can buy at the drugstore zinc oxide, the white stuff you paint on your nose so that you don't get your nose all sunburned. It doesn't say zinc 2 oxide on the back of the tube. It just says zinc oxide. Again, most chemistry textbooks will go ahead and put the Roman numeral 2 in for zinc, even though there is no other option available. So kind of be aware that those 2 are slightly different in that they have no alternative charge compared to pretty much all the other ones. Now, I will also mention here, there are a few elements that have more than 2. Chromium is one of those. Chromium 2 and 3 are the most common, but you can also have 4. Chromium 4 is a thing. And there's a few other ones that you may see if you look at a table that starts quoting oxidation numbers, which we won't get into yet. They're an extension of what we're doing in this chapter. But you will often see other charges for certain transition metals. So last set of binaries. Remember we said sometimes you get 2 nonmetals stuck together. Okay, back to the world of assumptions. Which are not wrong. We're gonna tell you to take it on faith right at the moment and come back later and tell you why it's true in another chapter. Chemistry tends to be taught that way. The initial phases, in a lot of ways, in terms of, not the dimensional analysis part, but a lot of the other things, you go, do it this way to start with, and then the deeper you dig, as you progress through chemistry, the more you begin to understand the why it's that way. So that's just kind of the way general chem's taught. We're gonna assume that when you have 2 nonmetals stuck together, that the first one is positive. But at the moment, take it on faith. Which then means assume the second one is the one that is negative. Now we're going to use prefixes. This is different. This is different than what we've been doing. These are also prefixes primarily that you would associate with geometry. Mono for one, di for two. Bi means something different. B, letter B as in boy, means something different in chemistry. Tri for three. And now here's one that's a little bit different in that in geometry, you have quad as in quadrilateral, but you also have tetra as in tetrahedral, which is another term we're going to come back to. And then you have, think like polygons, penta, hexa, hepta, octa, nona for 9. That's a little bit less common, and deca. For purposes of just general chem, we usually stop at 10. Yes, there are more, but we usually stop at 10. Here's a little hiccup in the rule. You're not allowed to use the mono prefix if the first element has only one. All right, so let's look at some examples. CCl4, carbon tetrachloride. Don't call it monocarbon, okay? You can't use a mono if it's with the first one. Carbon tetrachloride is a liquid. Carbon tetrachloride is a carcinogenic liquid, used a little bit still in organic chemistry, but not a lot. It has some industrial uses. CO. Now this is not cobalt because it's a capital C and a capital O. People don't think about why things are named the way they are. So carbon monoxide, the stuff that comes out of the exhaust of your car, okay, there's a reason why it's actually called that, because it has one carbon and one oxygen. You are allowed to use the mono on the second element if there is just one. Carbon dioxide, exhaust from people, okay? CO2, two different things, okay? Two slightly different molecules. What if you have multiples of each one? That's possible. N2O5. Dinitrogen. Remember, we're keeping the intact name of the first element. Don't put a suffix on the first one. Suffixes only go on the second one. Pentoxide. Most textbooks stick with the convention of drop a vowel to make it, in part to make it a little bit easier to pronounce, okay? Pentaoxide, I wouldn't necessarily call it wrong as not the usual way. Usually they drop the A so that pentoxide, just 3 syllables, it is a little bit smoother to pronounce. That is not true for iodides. Triiodide, if you had 3 atoms of iodine, and it looks really bizarre when you write it out because it's TRIIOODIDE. They keep the 2 I's in there because there's actually there's an extra syllable involved. Here's a couple more examples. You will see occasionally noble gases. Not a lot, okay? And not the top half of the column. Helium, neon, sometimes you see argon. But helium and neon are so tiny, their ability to bond with another atom is essentially non-existent. But xenon and argon, you will sometimes see with another nonmetal. So that's what I gave you an example here of xenon hexafluoride. You have a single atom of xenon and you have 6 fluorines all scattered around it. Later on down the line, toward the end of the semester, we will talk about the geometry of how this molecule is put together, because there is a method to the madness. Oxygen difluoride. That goes back to one where you have a single, don't call it monooxygen. Keep your DI for the difluoride. This should leave us about basically 2 sections left to cover in this chapter. So we will finish up this chapter on Thursday and also then probably get a little bit into chapter 3. This will make your chapter 2 homework set due 1 week from tonight. So, and I don't have a calendar immediately pop-upable in front of me. So whatever next Tuesday is, and I'll try to make sure I remind everybody again on Thursday, next Tuesday is when your chapter 2 homework set is due.
The
To
15th.
be the 15th.
Okay, that sounds about right. So like I said, I will go back and put that in as a due date, but we're relatively close to the end of the chapter. I don't want to, this is a lot of information. I kind of want to hold off on the last 2 sections of this chapter until Thursday to give you a little bit of absorption time. And yeah, be aware that I've done a whole bunch of weird rearranging on the way the Canvas shell is put together. Some of the stuff that is not turn in assignment stuff is now pages. So a couple people who logged in late, when you log into the Canvas shell, of course, there's the home page, which I think is kind of useless, except for the fact that it does tell you where specifically to go if you need the disability services applications. The rest of it is kind of the same for everybody. But do view all pages, and then it will show you, and they're alphabetical. Okay, I don't have any control over that. They're just alphabetical, or at least they're alphabetical from my end. I don't know if you guys see anything different. There's a whole page, then that's just notes. Should have everything but the chapter 7-8 notes, because I just transferred everything across. There's a page for answer keys. So as we progress through the semester, all of the answer key files will be loaded to that page. I'm going to try to pull all the videos onto a page, all the like little YouTube videos that kind of help you, just extra information kind of things. I'm probably going to try to put the handouts on a page over the next few days. The reason for doing this, and this is in part based because somebody told me I was doing it wrong, and I'm trying to fix it. Of course, they didn't tell me that I wasn't supposed to do it that way, so there is that. One of the things that's true about all of this is, if you had looked at, like, if you were looking to see what kind of a grade you got for the chapter 1 homework, you probably saw a bunch of columns that just said like out of 0, out of 0, out of 0, out of 0, because the way I loaded them into the system, it treated them like they were a gradable assignment. And so hypothetically, okay, fingers crossed, the reason for pulling all this stuff out and dumping it onto pages is then the only things eventually, hopefully, that will show up on your grade page are actual grades, and not just random columns of stuff that was just like notes and handouts and that kind of thing. So there is supposedly a reason for doing it this way. I will say once again, I hate Canvas. Blackboard was so much easier to use. Canvas is really, in my mind, kind of an almighty pain in the butt, but we are stuck with it.
You got it, probably.
So questions about what we've covered here in the middle of chapter 2?
I got one quick question.
Yes.
Just going back to, I was going back to, I think, page 9 on the notes and page 10. Are we just, when you're doing those, are we just adding those up? I got a little confused.
For determining your transition metals?
Yeah, I got it confused. Like you know, you got the aluminum +3, and then you got the aluminum. You got a +6, but then I got a little confused.
So when you look up things, okay, things that are not transition metals, you determine the charge by where they are, which column they are on the periodic table. 1, 2, 3, 4, 3, 2, 1, 0.
Okay.
That's the pattern. So anything that is not a transition metal, you can look up your column and determine what the charge is. And then you have to use just enough to make the pluses equal the minuses. Sometimes it's just 1 and 1, okay? But sometimes it's not. So it's like there's some examples in the notes. There's some examples in the textbook. There's a few examples in the lab book. And we are actually heading toward doing the dry lab, which is, I loaded a batch of stuff onto the lab shell, and it's in your lab book. And you can, since I see you guys every 2 weeks, you can ask me questions like, okay, B group I see 1 week from yesterday. And then A group I see again on the 21st. But send me email if you're stuck about like, I did this one and I don't know where I went wrong kind of thing. Send me email. Most of it's all about matching the charges though. You kind of have to give your brain, like read through it, give your brain a day to digest because it's a lot of information that has to be kind of synthesized together. Nomenclature is, depending upon how your brain works, okay? If you're a mathy person, chances are nomenclature makes you crazy and dimensional analysis is easy. Actually, if you're a language person, a lot of people who have like good language skills in terms of like, you know, learning foreign languages do really well at nomenclature because it's kind of like a language set. You've got nouns and verbs, which are kind of like cations and anions. So you have to make them match.
And one more. Doing the we was doing the what was that on the notes? To everything, and then when we doing the we had the prefixes, right?
Yes.
To everything in IDE. Is it like fluoride? Yeah, fluoride.
Up to this point.
Yeah. Okay.
Up to this point, everything in the second element ends in IDE.
Okay.
That's about to change though once we get to Thursday. This is a big chunk of information.
ATE.
ATEs and ITEs, and there are actually rules for them, but I will be honest, the rules don't help. It's memory and sort of grasping the way it is applied. There is a memory part to it. We're sort of embracing the brute force memory a little less so because we're all doing this online. And okay, so let me talk forward a little bit. Okay, I'm almost done typing the first test. This has taken me 2 weeks to type this test. I hate Canvas so much. The test will require you to use the Respondus Lockdown browser, which means you can't web surf. You can, however, use your notes in your textbook. There is no way, realistically, for me to make you do it otherwise. which also then slightly changes the methodology of my question wording, I guess you'll call it. But it also means that you will have a periodic table, and you will have your textbook, and you will have your notes available if you print yourself out a copy, such that you can use a little less brute force memorization, but you still have to know how to apply the rules. So that is coming. However, memorizing them helps, because being able to have them at your fingertips is really helpful, because they're not going away. Pretty much all the things that we learn in this chapter continue to pretty much haunt you for the rest of the semester, and next semester if you take second semester also. They don't really go away. Chemistry is cumulative. It's kind of like taking calculus. I hate calculus. I love chemistry. I'm not great at calculus. But like many things in math and science, there is a lot of cumulative stuff going on here. Other questions about that? Like I said, give yourself, okay, go back and read through the chapter. Go back and read through the notes again if you want. Digest some more of this information. Decide, scribble yourself down some questions. What you want to ask me on Thursday. It's like, well, I tried this. Why? Why does it work? Why does it doesn't work?
Gotcha.
Yeah, going forward into like a civil engineering program, how much into play does a lot of what you're trying to teach us, come into play on a regular basis?
In civil engineering, okay, not really truly my bag, but here's my thought on that. Because steel, concrete, things that electrical conduits are made out of, all of the things that are involved in the composition of the materials that get used means that there is a materials science chemistry component to civil engineering. If you're, okay, when the world is not ending, my kids usually, or my kid at this point, it's the younger one, not the older one, goes to co-op out in Suffolk, and I drive to Suffolk twice a week, which means I go over the high-rise bridge. And they're building that second layer off to the left-hand side. Knowing what kind of concrete, knowing what ratio of, okay, and I'm probably using the words wrong, the cement part to the gravel part, like what the component level has to be in, my husband contributed aggregate, knowing what the ratio has to be and what the cement has to be composed of in order to build a bridge over which semi-trucks can drive over safely. There's some chemistry as well as some engineering involved there.
It depends
So
on the civil
it doesn't go away entirely. It's applied a different way.
Yeah, that's what I do. It depends what kind of civil engineering you're going into.
Yeah. It depends on what your job ends up doing.
Yeah, if you go work for a municipality at, say, City of Virginia Beach, or you're doing sewer or water, you probably won't see too much chemistry or any at all. So
I imagine whoever develops a product, will, sell you it and give you the lowdown on it. But
it depends upon which end of the system you're in. That probably is about the best way I can say to approach it.
Okay.
I will be honest about this. It's what they call the weed out program. Okay. Engineering programs as a whole require 2 semesters of chemistry because the thought process, and I did not design this, okay, so don't shoot the messenger. The thought process is anybody who is getting an engineering degree should be able to get a C or better in any science. That is the brain train that the engineering programs use. Now, TCC does not use it to the same aggressive level in some degrees that, say, Virginia Tech does. If you take chemistry at Tech, you have to take chemistry for engineering students, which is designed to be a flunk course. TCC, we have so many different people funneling into our course. We teach general count, okay? What degree program you are eventually going into, we may or may not know, and it doesn't actually matter. We teach all the people who pass through the class the same basic set of information. So there is a little bit of difference between taking it at a purely engineering-ish school system versus taking it on a more more gen ed system is kind of the way it goes.
Okay. Well, that's good to know. It's good info.
ODU is slightly more aggressive at trying to flunk people out in chemistry than TCC, but not as aggressive as Tech is, or so I have been told.
Yeah, I could argue the merits of that, but
yeah, I have feelings on both ends. Like I said, the idea is supposed to be that if you're an engineer, you should be able to get at least a C in any science class. That's their kind of take on the deal. So, but on the other hand, I'm not sure why they should require it to be harder, other than the fact that they are trying to weed out the people who are never going to make it through Calc 3 and DiffyQ and tensor calculus and some of the other things. I think they're trying to like weed them out of the system faster. Is not a great idea, but I vaguely understand it. So, like I said, I am not in control of that end of it. Whatever your degree is headed toward, everybody gets the same information from our department. So I will see everybody on Thursday. Write yourself some questions, okay? Give yourself a night to digest, okay, about what all we talked about, and then think about what didn't make sense so you can ask me questions on Thursday.
Are you going to be putting a due date on the chapter 2 homework then?
Yes. I will probably either do that tonight or tomorrow. It will be 1 week from tonight. So somebody said it was the 15th.
yes.
The front page is stuff we already covered last week. The back of the page is nomenclature stuff, of not all of which we have covered yet. So we have not got through the end of the chapter yet. So you might want to start looking at it, but we have not talked about the last set of the rules.
Sounds good. Thank you.
Okay. I will see you on Thursday.
Have a good one.